Hi everybody, this is a lecture for the digital image. We will study more deeply on the digital images. In order to develop a successful object recognition system, we need to understand the digital image. This slide shows the process of digitalization of a video signal. The real world is an analog world, and we can see a continuous view of a world, and the intensity of each object is continuous. The digital camera or CCD camera can turn the analog image into the digitized image that has a discrete pixels and a quantized intensity. Thus, sampling and quantization and coding are happening in making a digital image. The digital image is made of a group of pixels. That means pixel. The name pixel means picture element. Picture element. So that makes name pixel. And the digital image can be have pixels of which size is 640 by 480 and 1024 by 960, so on. The CCD chip, this is a CCD chip, consists of a very small photo sensor cell. This is photosensors, and typically it is the size of this chip sensor is 0.01 millimeter by 0.01 millimeter, very small one. So if this CCD chip size, if CCD chip has 6.4 millimeter in width and 4.8 millimeter in height, so there are 640 cells in the row and 480 cells in the column, in one column. So okay, if there are 640 by 480 photosensor cells in the CCD chip, each photosensitive cell receives light on each photosensor area over here. Then it turns it into a single electrical signal. So they receive light and they turn it into electrical signal, a voltage. So during this process, an analog image is sampled into 640 by 480 pixels. So there are analog signal, light is coming out, and this is a continuous light, but when it passed through the CCD chip, they sampled by the 640 by 480 signals, voltages. So this slide shows the result of sampling. You can see the difference. So this is analog image. Then it is sampled to the discrete image. So when we use this is a 15 by 15 pixels. This image is they use the 30 by 30 pixels. So when we use more pixels, we will have the more smoother images, sampled images. So this is a result. Um, you can see this is a more better image than this image, right? So uh, we want to have more pixels in our camera. This image of a lady is very famous in computer vision area. The name of this image is Lena. Lena is her name, and almost all textbooks use this image to demonstrate the result of image processing. The three pictures of 60 by 64 by 64 and 128 by 128, this is a 256 by 256, shows the effect of number of pixels. We call it resolution. If you use more pixels, you can get a more smooth digital image with a higher resolution. So this number come from 64 is 2 exponential 6, and this is 2 7 2 8. So we will see much frequently about this number 64, 128, and 256. So please remember these numbers. The photosensor in the CCD chip can produce the electrical signal that is proportional to the intensity of the light. So here is intensity of light, that is analog signal, and CCD chip photosensor can produce the voltage that is proportional to the light intensity, and this voltage is also analog signal. You can see the smooth analog signal of the voltage. So you need to quantize this analog image into some digital quantity. So from here to here, this is analog intensity. So from here to here, it mapped to 0, and from here to here, it mapped to another level. From here to here, this is another level, mapped to another level. From here to here, it also mapped to another level. So the continuous signal is mapped to the limited number of the value. This is quantization. So you can see difference between 10 levels, 12, 20 levels, and the 40 level quantization. So if when you use more levels, then you will get more smoother images. This image shows the effect of quantization. This image uses 2 levels, black and white, and image B has 4 levels, and the image C has 16 levels. Image D has 256 levels. This is a typical grayscale image that use 256 levels. Each pixel has pixel value between 0 and 255. So there are 256 levels here. The 0 means black, 255 is white. In the middle of this number, it is gray. The 2-level image is usually used to recognize some object. If we have an image like this, and here is an object, the histogram, the intensity is from 0 to 255. So this is a black, this is white. So there are some histogram like this. So this is a background, this is object. Then by thresholding this some level, so we can tell this is object and this is background. So we make a grayscale image into two level image by thresholding. Thresholding the image. So we will meet two level image later, and we will study thresholding later. After sampling and quantizing the image, each pixel has its own intensity number. This example shows the 4-bit number to express the 16 levels of intensities. These numbers can be coded to compress the size of the image. So the force power of 2 results in 16. So using 4 digits, we can express 16 levels. So this is this shows a 4 digit, and the number is a 3. This number is a 1. This number is a 2. This number is 1, 2, 4. That is a 5. So this pixel is the brightest pixel here, and we can compress this digit to save the memory. So there is a JPEG and some many other compression format in the digital image. If you are interested in the image compression, you can visit Google and search for the image compression object. Okay. The uncompressed image is called a bitmap image or the raster image. A raster image has an x-axis that starts from the left top corner of the image and to the right direction. And the y-axis has the same origin as the x-axis, then it going downward of the image. However, if we have some matrices 640 by 480 matrix, that means this column they have 640 column and 480 rows. So the matrix, the Korean name of matrix is Hangryul. You know the Chinese character. Hang means row, Ryul means column. So traditionally we call row first and column later. So if we specify the array position 10 100 by 300, then this is a row, this is a column. So we have 100 here, 300 here. This point is 100 by 300. This is a array position. However, the axis is like this. This is x-axis, this is y-axis. Image coordinate is x comma y, x comma y. So this length should be calculated, and this length should be calculated. This length is x, so it is related to the column number. So there is a C1 column. Then we can calculate x length using C1 information and put here the first axis number, and there is a row. So we should calculate row information and the y axis value. This is y, and we put number here. So image coordinate and the array position is different. For example, 100 by 300 array position, and this is image. And if there is a CCD chip that has a 6.4 millimeter in x direction and 4.8 millimeter in y direction, so each pixel has a 0.01 by 0.01, very small pixel. Then so 100 pixel means it's a 100 pixel by times 0.01 is 1 millimeter. 300 pixel by 0.01 is 3 millimeter. So image coordinate is 3,1 in millimeter, and that pixel position is 100 by 300. This is a row and column, and this is x direction and y direction. So these are different. Thus the digital image is expressed as the intensity array I x comma y, where x is a column number and y is a row number. So for n by m matrix, there is a m by n by m matrix. The column number starts from 0. Here is 0 and n minus 1. So there are n column, and the row starts from 0 to m minus 1. So there are m rows. So I x comma y means that is column and the row, that is intensity value at the column comma row. So this is the expression of the bitmap image. This picture shows the binary image. Every pixel has a 0 or 1. Here is 0, here is 1. Black or white. The 0 is black, white is 1. Or this is 0 or 255 in 8-bit image, but in 2-bit 1-bit image, 0 or 1 is only option. The left image is a flamingo expressed in black, and the right image is a H image. This is H image of the flamingo. This picture shows a gray image. Typically 8 bit per pixel is used. Thus there are 256 levels in intensity in a pixel. 0 level is a black and the 255 level is a white. The level 147, or 151 is all gray. So this is all gray value. What is the highest, brightest pixel in here? So 159 is the brightest one, and 146 is the darkest image. Okay. This picture shows a color image. A color is expressed in 3 components: red, green, blue. 3 components. The 3 grayscale image for each component are needed. So this is a grayscale image for red. This is grayscale image for green. This is grayscale image for the blue. So for this, the same pixel, it has 217 in red and 57 in green, 37 in blue. What color is it? The red color is dominant, so you can see the very reddish color here, and there's 8 bit for each component. Thus there are total 24 bits are needed to express the color. So 8 bit for red, 8 bit for green, 8 bit for blue. So total 24 bit is required. So there are 8 power over 2 times 8 power over the 2 times 8 power over the 2. Total 16,777,000 16,777,216 colors. 6 billion colors can be expressed using the 24-bit color. These 3 grayscale images are for red and blue and green. So by combining these 2 grayscale image, then we can get this color image. So for express the blue, the red is 0 and the blue is white and the green is 0. So there is only one blue color is here. In order to save the graphic memory, many systems use the indexed color image instead of true color using 24-bit. Human eyes can differentiate the limited number of colors. Thus, instead using the true color of 24-bit, they use a lookup table with the limited number of color that human can differentiate. For example, this pixel has index 10. So this picture has index 10 and the 10 does not have RGB information. Instead, this is indexed to that color. 220 and 60, 40. This is a reddish color. So this is a lookup table. The lookup table has RGB information and the index number, and in each pixel has only index. So it does not require that many memory, because the number of color is much less than the true color. Before we learn more about the digital image, we need to study hexadecimal numbers. In a decimal number, each digit has its own positional number. 3, 2, 1, 2, for example. This is a positional number. There's a 10, 10 square and 10, 1. This is a positional number, and we multiply this number to the positional number. So we use a number from 0 to 9 to express the decimal number. Hexadecimal number, that is a 16 digit system. So 312 in the hexadecimal system, we express 312 using OX number. So this is the symbol. That number is a hexadecimal number. And this is a positional number. This is 16 square and 16 and 1. So we multiply 3, 1, 2 here. Then we can get the 785 in decimal number. In hexadecimal number, we use from 0 to 9 and A to F. A means 10, B means 11, and F means 15. So when we add one more number, that becomes 16, and they go to the greater position number. Okay, so another usage of hexadecimal number is to express the bit value with a compact form. If there is a 1 byte value whose binary number is 100101111. So what is number in hexadecimal? So 1 byte is 8 bit. So 8 bit can be divided into 4 bit and 4 bit. So we divide this number in two group, and 1001 in binary number. So we turn it into the hexadecimal number easily. That is 1, 2, 4, 8. So this number 1001 is 8 plus 1, so it is 9. 0111 is 4, 2, 1, so it is become 9. So we can easily turn this number into the hexadecimal number, and we can turn it into the decimal number by multiplying 9 times 16 plus 7. That is 151. For this example, 1111 is F, that is 15. 15 is F, and the 0010, it is number 2, F2. It is 242 in decimal number. This slide shows the structure of a bitmap BMP file. Bitmap picture file is one of the popular image format in the computer vision area. There is a file header at the top of the image, then bitmap info header, then LUT lookup table follows. Then finally image data is attached. This is the file header, which include file type, and this is always a BM for the BMP file. That means BMP. BM means a BMP file. So B, the ASCII code is 42. M's ASCII code is 4D, and next one is file size, and the reserved areas. There are two reserved area. It is always 0, and pixel offset number. So you can visit here if you find more information on the BMP file format. This slide shows the example of the color BMP file. So this is the header of the BMP file. Okay, so this is a file header is up to here. So this is a magnification of this area. First two digit 442 and 4D is ASCII code of the B and M. ASCII code okay. ASCII means the American Standard Code for Information Change. The acronym of this name ASCII is ASCII. ASCII is the name of this full name. And ASCII encoded 128 specified characters into 7-bit integer as shown by the ASCII chart. The character can be expressed with a decimal or hexadecimal number. So this is a decimal number, and here is a hexadecimal number. That is a character expressed by the number. So for example, A starts from 41, B is equal 42, and M equal 4D, etc. So here next 4 byte is file size. However, it is a little endian. There is a little endian and the big endian. There are two types of expressing the number. The little endian, this is the actual number of the file size, but the smallest digit comes first. This is a little endian. This is for the efficiency of calculation. So in this system, they use a little endian system. The C8 B00000 means this is the big digit is 0 0 B0 C8. So this is a file size. B means B in hexadecimal number is 11, right? A is 10, B equal 11. So this is 1, 2, 3, fourth positional number is 6. third power of 16. So 11 times third power of 16 plus this is 0, and the c is 12 times 16, and there is 8. So when you calculate this number, 45,256 byte. So it is about 45 kilobyte image. The reserved areas are 2 reserved area, and this is the end of header. This is offset number. This is also little endian, so the number is 0 0 0 0 0 0 0 36 in hexadecimal. So the end of header is 36 position. So this is 1 2 3 4 5 6 7 8 9 10 11 12 13. This is 16 byte here. This is 16. So 1 2 3 row, 3 6 means 3 row, and 1 2 3 4 5 6 byte more byte. So after 3 rows and 6 byte, then the header ends, and from here it is image data. Then up to here it is a file header. Then from here it is a bitmap info header. Bitmap info header has this kind of data. The structure, the size of structure, and the width and height of the image, bit plane number, that it should be always 1. Bit count, that means the number of bit per pixel. So maybe it is a 1 bit pixel, and 4 bit, 8 bit, 16 or 32, something like that. So 8 bit has 255, from 0 to 100, 255 levels. Okay. Image compression, if there is image compression, you use this word. And bitmap data, size of image, bitmap size of image, and this is horizontal resolution, and this is vertical resolution, and this is LUT color lookup table, something like that. The first, this 4 byte 28,0,0,0 means this is a minimum size of a header. So 28 means 2, 16 by 2 is 32, plus 8 is 40. Okay. So I think this is 28 in hexadecimal, means there are 2 rows here in the 8 byte, 1 2 3 4 5 6 7 8. So from here 28 in hexadecimal byte, the header ends. So from here it is image data. And 96 and 64 is width and the height of the image. What is 94? 94 in hexadecimal means 16 by 9 is 144 plus 9. Oh, 64. Oh, no, I'm sorry. 64 means 16, 6 is 96 plus 4 means 100. So width is 100. Height, this is height. Height is 100. 96. Okay. Oh. 96. 16 by 9 is 144 plus 6 means 150. So width is 150 and height is 100. Oh, I think the width is 90. Okay, yeah, this is the size of image, and one is a bit plane. It is always one, and there is a 18 bit is used, and okay, so the detailed number you should visit Google, and you can find more information of bitmap. This slide shows the example of two bitmap files for a color image and grayscale image. This is the total ASCII code table. So they can express this character from null to start of heading, something like that. So they can express the special characters and the numbers and some symbols, and they express the capital alphabet and the small the alphabet and the del. So they can express 128 special characters using they express 128 special character using ASCII code. So up to here it is a header, and this is the first pixel of the image. The BMP file, image file, coordinate is lower left corner. So this is x-axis, and here is a y-axis. This is the first pixels. So original pixel is 36 4a 59 in hexadecimal. When we turn it into the decimal number, that is 54, 74, 89. So it is a gray, little bit. It's a gray, and but red is a little bit higher. The green is higher than the blue, so it is a greenish gray color. So when we switch the number into the 00FF, FF means 255, 00255, this is R, B, G, so this is a red color. When we switch this gray color into the red color, we can see the red dot here. Okay. If we have a two-dimensional BMP file here, there is 10 bytes in width and 8 bytes in row. So we can express this image using two-dimensional array, but sometimes we turn it into the one-dimensional array value. So the x comma y image can be expressed in the one-dimensional array. We multiply width by y value. So this is x, this is y. So when we increase one y, it requires one width value. So by multiply y to width value plus x is corresponding position of the two-dimensional array x comma y. So data 1, 2 means data 12 that comes from 1 times 10, that is width, plus 2. So in one-dimensional array, data 12 is corresponding. When we consider 150 by 50 image with 8-bit grayscale image, there should be 150 and 50. So there are 150 column and 50 rows. So if there is a x comma y, so we can make this two-dimensional array into one-dimensional array using this equation: width times y plus x. So for example, x comma y equal 2 comma 1, that means there are the second row and the first pixel. That means we know that the width is 150, so that 150 times 1 plus 2, that makes 152. So it looked like a correct answer, but in BMP file it is wrong, because the width should be the multiple of the 4 byte. So 150 cannot be divided by 4. So it cannot be divided by 4. So the next number that is a multiple of the 4 byte is 152. So we should use the width 152 instead of 100. So that is the end of the file, the first row, but we should use 152 as a width. So there is a two empty space here. So the 2 comma 1 should be 102 times 1 plus 2, so that should be 154 is correct one. So this is equation that make the width as 4 times multiple of the 4. So if the width is arbitrary width of the image here, then width step is multiple of 4. So for example, previous example width was 150. So 150 plus 3, that is 153, divided by 4, so that is 38. That is, this is integer calculation, and 4 times 4, it is so this number is 152. So using this equation, then we find out the width step, that is a multiple of the 4. So we can use this width step instead of width. So okay, this image is output of a vertical flip software. So in 2D original 2D image can be switched to the one-dimensional array. They use the width step, and instead of y, they use height minus y in order to flip the image. This is example code for the flipped image. So actually we will not use the bitmap file in our OpenCV programming. So the OpenCV supply the matrix M, so they save us from this troublesome calculation, and they provide us a very simple and easy way to handle the bitmap image. But this is some example of the computer vision software that is not using, they are not using the OpenCV. They use window.h, so it is a very complex and troublesome. Okay, they open the file, and they checked it is whether it is BMP file or not. So they checked 4042. So if it is, the first byte is not 4042, it is not a BMP file. And they check several times, several things, and they check the size, and they checked whether it is a 4-bit grayscale or not. Then they read the file, they read the lookup table, then so they allocate the memory, they calculate output image using width step, Oh, this is not a flipped. Uh, Output is not a flipped image. This is a uh, what is that? They make the white to black, black to white. So they make the color image. Then they make a negative image film. Oh, actually it is not color. It is a grayscale image. Negative image. They create negative image. So please don't mind on this software. This is not OpenCV. It is OpenCV is much easier than this software. So this program is to show the bitmap structure and the calculation of the bitmap image. So we will study OpenCV from next class, and please finish your reading assignment up to chapter 2. Okay, see you next week. Bye bye.